This is a continuation of the discussion we had previously on linearization, and today we're going to be discussing the other half of this section, Newton's method. If you recall, linearization was building up a model or an approximation of a function using straight lines, and this model is very useful for us in approximating values, in coming up with models for complicated functions. However, it's kind of fallen by the wayside because of the need for those tools being lessened by the fact that we have graphing calculators. But just as a reminder of what we came up with yesterday, recall that this is one way to express a linear model or a linearization of a function about a particular point. This would be the linearization of, so this is the linearization of f of x about x equals a. We're actually going to be using this today when we look at Newton's method. Newton's method is based on a linear model, or a model of the linearization of functions. However, what Newton's method does, the goal of Newton's method is to approximate the zero. So Newton's method is an iterative process. That means we do it over and over again, and the more we do it, the closer we get. This is an iterative process for determining the roots of functions. Not just polynomials, but any kind of functions at all, anything we can take the derivative of, with some exceptions. We'll see later on some of the issues that Newton's method presents in certain situations. To illustrate a little bit what's going on with Newton's method and to give you a visual picture, I actually have an example here of a function, and we're going to discuss a little bit about what linearization and Newton's methods will look like here. This function is the function x squared minus 2, graphed on the interval from 0 to 6 roughly, and you can see that this is a very parabolic sort of shape. What I'd like you to notice is on the x-axis you can see a dot. That dot represents an initial point. I can use this slider to move the dot back and forth, and we're going to set that dot at some initial position. In this particular case, 4.99. And what we're going to do is we're going to linearize the function x squared minus 2 at this point, 4.99. So I'm going to simply click up here, switch this to n equals 1, and we're going to come up with the linearization of this function. Now, if you'll notice, the linearization it's a function that has a positive slope, but one of the interesting things to notice is where the x-axis intercept is. So we can see here that the x-axis intercept of this particular function, this linearization, is over here. Notice that it's fairly close to the root. If I change the value that we're starting from, so if I were to look at a different value, notice that in all of those cases, the x-intercept of the linearization, so this point right here, this x-intercept is approaching the root of this particular polynomial. Notice that it gets a little bit closer. The closer my function is, the farther away the initial point is, the farther away the x-intercept is. But it gets closer and closer. And if I shift my function now, if I choose my point to be on the opposite side, notice that the intercept does in fact go towards the root. It actually, the x-intercept for this particular point here, the linearization, that point intersects over here well past 3, but it does point towards this particular, it does point towards the root at any rate. So the way that Newton's method works is if we start with some particular point, and we'll go ahead and just for the sake of argument, we'll choose 5.75. You will notice that the function, the linearization, generates a line, and the line has an x-intercept here close to 3. what we're going to do next is we're going to take 3 as our point, and we're going to produce a linearization of this polynomial about 3. And notice that when we do that, that gives us a linearization that has an x-intercept that is closer to the root. And we can continue to do this. So we can take our next linearization and so on and so forth. And we can do this, and our results will get closer and closer and closer to the root. So this method of using linear approximations to get closer and closer to the roots, this is what Newton's method is. Now notice that if we do this on the other side as well, so we'll bring our point over to the other side here. Notice that even though our initial point actually ends up being quite far from the root, if we then follow Newton's method, if we then take successive approximations of these linearizations of the function, that gets us to the right answer. So this is what we're going to be looking at. This is the technique that we will make use of today to work with Newton's method. And like I said, this comes about from the process of linearization. So let's look at the way that things are going to work here, how we're going to apply linearization. So I'm going to just draw out a sample function, and we'll go ahead and make it a function similar to the one that we saw there. What we're going to do is we will be starting with an initial x value. We'll be starting with an initial x value. That initial x value will give us an initial y value, and we'll go ahead and we'll construct the linearization about this point. So we have the linearization of x is equal to f prime, the derivative at x0, times x minus x0 plus f of x0. So this is simply the formula we saw last time. This is the linearization of this function. However, what we want, remember, is when we construct the linearization here, what we want is this point right here. We want this point which has a y value of 0. In other words, if this line here represents the linearization of x, what we want to do is we want to figure out when is the linearization of x 0. And it turns out that we can use this equation to solve for that. We can find out when the linearization is 0 simply by setting this function equal to 0. So we have f prime of x0 times x minus x0 plus f of x0. This represents the equation for the linearization of this function, and we're finding out where this intersects the x-axis. So we can simplify this expression first of all by moving the f of x naught over. So we have minus f of x naught. That will equal f prime of x naught times x minus x naught. And what we're solving for here is x. We want to find the x value where this crosses the x-axis. So this becomes minus f of x0 divided by f prime at x0, and that will equal x minus x0. Or x must equal x naught minus f of x0 divided by f prime of x0. So this particular equation right here tells us where the x value is that our linearization touches the x-axis. So to come back up here and look at our work previously, this is the x value that we found. This value right here, that's the x value that we found in setting the linearization equal to 0. Notice that that is closer to our root. And what we're going to do next is we're just going to repeat that process. We're going to take this value and we're going to come up with a linearization for this. And that's going to give us a new x point, and we can continue doing this as often as we need to until we get acceptably close to our root. Okay. But what that means is that we're going to repeat this function over and over again. We're going to keep putting things into this over and over again. So this is the function that we're actually going to iterate. We're going to repeat this process. And so there's a better way of writing this function. We'll go ahead and write this out in a little bit better way, one that will make more sense in the way that we're going to do this. And that is that our new x, that is the new approximation to the root, our new x is equal to our old x minus the function value at the old x divided by the derivative of the function evaluated at the old x. So what we need to do is we need to choose an old x. We need to choose a starting value. Okay, we need to choose a starting value. We plug that into this function, and we repeat this until we end up with a value that is close. Okay, a value that is useful. So let's do an example of this, because this is a fairly complicated technique to use.